US Physics Olympiad, year 2020, USAPHO, final round. This year, all competition was divided by two parts. Part A consists of 3 problems, and Part B consists of 3 problems. For each part, it was given 90 minutes. If you want to get more interesting problems, just subscribe for this channel. Problem A1. Breaking up. An infinitely long wire with a linear charge density negative lambda lies along the z-axis. An infinitely long insulating cylindrical shell of radius a is concentric with the wire and can rotate freely about the z-axis. The shell has a moment of inertia per unit length I. Charge is uniformly distributed on the shell with the surface charge density lambda over 2 pi a. The system is immersed in an magnetic field B0 in direction z and is at rest. Starting at t equals 0, the external magnetic field is slowly reduced to 0 over a time t much greater than a over c, where c is the speed of light. Question A. Find an expression of the final angular velocity omega of the cylinder in terms of the symbols given and the other constants. Question B. You may be surprised that the expression you find above is not 0. However, the electric and the magnetic fields can have angular momentum. Analogous to the regular angular momentum definition, the EM field angular momentum per unit volume at a displacement r from the axis of rotation is cross product of r and p as a function of r. P is a vector analogous to momentum given by P equal alpha multiplied by cross product electric field by magnetic field, where alpha is some proportionality constant. Find an expression for alpha in terms of given variables and fundamental constants. Solution for problem A1. Question A. Find an expression of the final angular velocity omega of the cylinder in terms of the symbols given and the other constants. Solution. First, we can use Faraday's law to find what is electric field induced inside cylinder due to change of magnetic field or magnetic flux. It states that integral around circle with radius a will give us change of flux through this circle with a negative sign. That will be 2 pi a multiplied by electric field on distance a equal negative pi a square multiplied by delta b over delta t, or electric field equal negative a over 2 multiplied by delta b over delta t. Next, we can count what is total torque from electric field to the unit of cylinder. That will be total charge, which is 2 pi a multiplied by lambda over 2 pi a multiplied by electric field and multiplied by distance from the center of this cylinder, which is a. And that's equal to moment of inertia multiplied by angular acceleration, which is delta omega over delta t. And now we can put this induced electric field in this equation and find what is equation. We have exact proportionality, that the change of omega proportional to change of magnetic field with the negative sign, and this is a coefficient of proportionality. And now we can just integrate both parts and put limits. Initial omega is 0. It means that formula will be omega as a function of time equal this expression, and finally, because final magnetic field is not 0, but it will be produced by appearing current from a rotating cylinder, and we can count what is this final B. Due to Ampere law, we can count what is integral through any loop like this. Magnetic field multiplied by delta L, and that's equal to mu 0 multiplied by total current through this loop. And here we can use the same technique as for counting what is a magnetic field inside solenoid. If we take a loop like straight line outside cylinder and straight line inside cylinder near the surface of the cylinder, outside magnetic field is 0, and here we just have due to symmetry magnetic field is a constant, and we have total current equal lambda over 2 pi a multiplied by omega and multiplied by radius a. Using this formula we can find that magnetic field proportional to omega and equal to mu 0 lambda over 2 pi omega. And now we can put this expression for magnetic field in our previous formula and find what is final omega for time when total external magnetic field becomes 0. So that will be omega equal this expression, and after that we can take omega out of scope, and finally omega equal this expression. This was solution for question A. Solution for question B. In our case, electric field created by a central wire is negative lambda over 2 pi epsilon 0 r multiplied by unit vector from this direction from wire, and the magnetic field is just B as a function of t in the direction of z. Now let's count what is vector p. That will be this cross product, or alpha multiplied by lambda b over 2 pi epsilon 0 r and multiplied by unit vector in the direction perpendicular to r and z, which is theta. And finally, angular momentum per unit volume is this expression, which is a negative alpha lambda bt over 2 pi epsilon 0 in z direction. Angular momentum per unit length we can just count multiplying this vector by cross-sectional area, which is pi a square. That will be this expression. And now let's find out what happened in question A. In question A we had delta omega over delta t equal this expression, and from here we can count what is a change of mechanical angular momentum per unit length. That will be I delta omega equal negative lambda a square over 2 multiplied by delta b, change of magnetic field. If we compare it to previous expression for electromagnetic field, we see that as much momentum we're losing magnetic field, as much we're getting in mechanical angular momentum. And this is true when coefficient alpha equal epsilon 0. So that was a solution for question B.